We've done Newton's first law, we've done Newton's third law, it's now time to do Newton's second law of motion. And this is where we're going to deal with acceleration. So we've been pretty much balanced in most of our force diagrams. Everything's either been at rest or moving at constant speed. That's all going to change now with Newton's second law. Before we define Newton's second law, we need to look at net force. Net force is the total amount of unbalanced force on an object, so it's the sum of all forces that cause an object to accelerate. If you have no acceleration, which is what Newton's first law deals with, then forces are balanced and the net force is zero. The symbol for net force, you can either use F with a subscript of net, F net, or you might see sigma F, and that just means sum of the forces. Sigma is a little bit harder to draw, so most of the time you'll see me using F net. That seems to be what most people like to use. But if you ever see sigma F, that's saying the same exact thing as net force. So if your net force or sum of the forces is zero, then there is no acceleration, forces are balanced. Otherwise, Newton's second law is going to deal with an unbalanced net force. So here we are, Newton's second law of motion. The net force of an object is equal to the mass times the acceleration. So Newton's second law is the equation. So the definition is the equation. F net equals ma, where F net is net force, m is mass, and a is acceleration. In honor of Star Wars, F net equals ma is the same thing as saying may the F equals ma be with you, so may the force be with you. It's coming out soon. I don't know if there's any Star Wars fans, but whenever you see those t-shirts, may the F equals ma be with you, you know now what they're talking about, if you didn't already before. You can also view Newton's second law, same definition, just telling you that the acceleration of an object is equal to the net force divided by the mass. So it's just this equation rearranged where A equals F net over mass. Same exact thing, just this time solving for acceleration. Newton's second law is also going to tell us what's inside of a newton. So if we're breaking down the unit, we're going to look at the equation F net equals ma. Force is measured in newtons, mass is measured in kilograms, acceleration is measured in meters per second squared. So by definition, a newton is 1 kilogram times a meter per second squared. And this comes right out of the equation from Newton's second law, just looking at the units. So if I ever say what's a newton made up of, it's a kilogram times a meter per second squared. Okay, so Newton's second law and force diagrams. Almost all of the force diagrams in the last unit dealing with Newton's first and third law were balanced. Not all of them, but the majority. These force diagrams will not be balanced, and you're going to know which way the acceleration is based on the longer arrow. So the longer arrow, wherever the unbalance is in favor of, will show the direction of the acceleration. If the arrows are either balanced or shorter, then there's no acceleration in that direction. To find net force from a force diagram, you're going to take top minus bottom or right minus left. So any force diagram, let's just say we have a book lying on a table, a book accelerating across a table. If we have normal force going up, gravitational force going down, let's say we've got a contact force to the right and a frictional force to the left. My net force will equal right minus left, so FC minus FF. In the y direction, the book's not accelerating, so Fn equals Fg, and the net force in the y direction would be 0. Okay, so to summarize, 2 ways to find net force. First is using the equation. So given mass and acceleration, F equals ma. Second way is with a force diagram. So with the force diagram, figure out where your unbalance is, top minus bottom or right minus left, and if those arrows are equal in the force diagram, there's no acceleration and therefore no net force. You have 5 example problems, I believe, after, sorry for the text message. I'm sorry, 6 example problems after these notes. I'm going to do numbers 3, 4, and 5. It's pretty much one problem altogether. 1 and 2 are fairly simple, just using the equation F equals ma. Number 6 you can do easily if you can understand 3, 4, and 5. So I'm going to do the problem with the elevator. It's a 3-part problem just to show you how this works, and then we'll be doing a bunch of practice. Okay, number 3 tells us an elevator is accelerating upwards. If the tension in the cable pulling the elevator up is 30,000 newtons and the mass of the elevator is 2,000 kilograms, find the net force on the elevator. So first thing we want to do is draw a diagram. Here's the elevator. It's accelerating upwards. Next, we want to list what we're given and what we have to find. We know that the tension force on this elevator is 30,000 newtons. We know that the mass of the elevator is 2,000 kilograms. And we're looking for F net. So first thing we need to do is draw a force diagram after diagramming give and find. We know that the elevator is accelerating upwards. So the unbalance has to be in the direction of the acceleration, which means that my tension force going up has to be longer than my gravitational force going down. It tells us that the tension force is 30,000 newtons, and my weight is easily found once we have the mass. So remember, weight is not measured in kilograms, weight is measured in newtons. So we're going to take our 2,000 kilograms times 9.8 newtons per kilogram, and our weight would be 19,600 newtons. So looking for the net force on the elevator, remember, 2 ways to find net force. The first way is using the equation F equals ma. We don't know mass, we do know mass, we don't know acceleration, so that's not going to work. The second way is by using the force diagram. So from the force diagram, net force equals either top minus bottom or right minus left. In this case, there's only vertical forces. So F net equals Ft minus Fg. This is 30,000 newtons minus 19,600 newtons. 30,000 minus 19,600 equals 10,400 newtons. Only one sig fig, so my net force is approximately equal to 10,000 newtons. So this is an example of using the force diagram to find the net force. Okay, now let's look at number 4, which is a continuation of this problem. And in this case, we're looking for the acceleration in the previous problem. I already have diagram give and find. I found my net force to be 10,400 newtons. And I want to use my unrounded number. I know that the mass of the elevator is 2,000 kilograms, and I'm looking for acceleration. F net equals ma, so A equals F net over m. So this equals 10,400 newtons divided by 2,000 kilograms. My acceleration is equal to 5.2 newtons per kilogram, which is the same as a meter per second squared. And either one would be okay in terms of units, so either newtons per kilogram or meters per second squared, they do equal each other. 1 sig fig, so A is approximately 5 meters per second squared. This number is positive because the acceleration is directed upwards. Had the acceleration been directed downwards or to the left, the number should have turned out negative. Because it turned out positive and it was going up, we know we did something right. And now for the last part of the problem. So a person standing on the elevator, the same elevator, has a mass of 65 kilograms, and we want to know what is the normal force on that person. So now we need to draw a force diagram for the person. If they're standing in the elevator, they're going to have their weight, Fg, and since the elevator is accelerating upward and that person is in the elevator, that person will also be accelerating upward, so they're going to have a longer normal force. We know for the person that the mass is 65 kilograms. We know that because the person is in that elevator, their acceleration is the same as the elevator's acceleration, 5.2 meters per second squared. And what we're looking for is the normal force. You're going to see a few problems where a person is in an elevator and they're asking for normal force or scale reading. Know that normal force, anytime you see it, is the same thing as either scale reading or apparent weight. So you'll see problems where a person's standing on a scale and they see this weight. That's their normal force, because that's telling you how much the ground is pushing up on you while you're standing on that scale. The reason I say apparent weight is because your normal force can change. And we will be doing a lab when we go into an elevator on a scale and we look at what our weights are. And you'll notice that your weight or in the scale, your apparent weight or the scale reading changes. So anytime you're dealing with a problem on an elevator and it's asking for normal force or scale reading or apparent weight, know that those three things are interchangeable and it's all asking for the same thing. So essentially what we're looking for is how much that person feels like they weigh when they're on the elevator. And if you want to think of it this way, you're on an elevator, you're going to notice your weight changing even without a scale. If it starts to slow down towards the top, you're going to feel lighter. As soon as it starts accelerating positively, you're going to feel heavier. So if you have a positive acceleration and your force diagram looks like this with a longer normal force, your normal force is going to be greater than your actual weight. If your normal force was smaller, then your normal force would be less than your actual weight and you feel lighter. Alright, so aside from that little discourse, let's now go back to the problem. You have mass, you have acceleration, you're looking for normal force. From the force diagram, so let's see, right off the bat we can figure out what our FG is, so 65 times 9.8 is going to give us our actual weight, which is 637 newtons. We don't know what the normal force is, but given mass and acceleration, we can figure out our net force, and we know that net force is going to equal, from the force diagram, normal force minus weight. So net force plus the weight will give me my normal force. We also know the second way to find net force is using the equation F net equals ma. So my net force plus my weight will equal my normal force. So mass, 65 kilograms, times unrounded 5.2 meters per second squared, plus my weight, 637 newtons, equals the normal force. 65 times 5.2, so this is 338 newtons. Again, meters per second squared is the same as newtons per kilogram. Those units will become newtons. Plus 637 newtons equals Fn. So the normal force equals 975 newtons. 1 sig fig, Fn is approximately 1,000 newtons. Normal force should be greater than the weight. Think back to the force diagram. The top was larger than the bottom. So if you saw this and you got something that was less than weight, you went wrong somewhere. Because of the positive acceleration, the man's going to feel heavier, or person, it doesn't say what it is. The person standing on the elevator is going to feel heavier as the acceleration is upward. So therefore, normal force or apparent weight will be greater than actual weight. If you feel okay with this, we're going to do practice tomorrow in class and a lot of other practice. So if you have questions, please come with them. Otherwise, we'll get ready to do lots of problem solving dealing with Newton's second law.